So apparently I stopped my recording by accident right there. So hopefully you have watched the end of the last video and you can go jump right into here. So again, we're talking about projections. We have these x and y, and I was explaining how what I meant by talking about we want the part of x that's going parallel to y and the part that's going perpendicular to y. So let's draw a picture here. We have Actually, maybe I make this a little shorter. We make our vector y, we have our vector x, and we want to kind of break x into two parts. Part that is going in the same direction of y, and part that's going perpendicular to y. So we'll have part of it down here, part of it there, and if we add these two vectors together, we're going to get the vector x. Let us actually name those vectors. We're going to call this z over here, and we're going to call this p for projection. So the idea is that x is the sum of p and z. P is parallel to y. It's in the same direction of y, or if this angle between x and y is obtuse, it can actually be the other direction. We can actually have a situation where we have our y here, we have our x here. We can project down onto the line that y makes. We get a vector that's the opposite direction of y, but still along that same line. That's what we really want. In this case, our z is still perpendicular to y, but we're in one of these two cases. Or I guess technically there's also the case where x is actually already perpendicular to y, and in that case the projection is just going to be the zero vector, because it's just going to, if we just drop a perpendicular, we're just going to drop it down to where x started in the first place. But we can always set it as x equals p plus z, where p is in this is parallel to y. Let's say it's parallel to y, and z is perpendicular to y or orthogonal to y. How do we find out what p is? Well, let's take the inner product, or the scalar product. Take the scalar product of x transpose, that should be a transpose, sorry, a t, x transpose y is x, well, we're going to replace that with p plus z transpose y. But this is just p transpose y plus z transpose y. P transpose y, well, remember p and y are parallel. So this is going to either be, actually, we'll have two cases. We'll have the product of the magnitudes of p and y, or negative the product of the magnitudes of p and y, if they're in opposite directions. But then z transpose y is 0, because z is orthogonal to y, and that's what our definition is. So we can solve. We can solve for the magnitude of p is x transpose x transpose y divided by the magnitude of y, and I'm going to, and this is what the book does. It's either plus or minus technically if we're in this case, but we're just going to look at this value here without the plus or minus. We are going to call this the scalar projection. This is a scalar projection of x onto y. And it's essentially the length of the orthogonal projection, the length of what we get when we drop a perpendicular from x onto y, but then just kind of keeping in track whether or not we are going the same direction or the opposite direction, whether or not this is actually a positive or negative. What if we actually want to find out what p itself is, though? Well, now we're going to have to include not only the magnitude of p, but we're also going to have to talk about the direction of p. Well, the direction of p is, we're going to get it by finding the direction of y. But remember, we need to talk about the pure direction. We don't want to have the magnitude of y come into play here. So we're going to make a unit vector. We're going to call it u. We're going to take y, we're going to divide it by its magnitude. This is now a unit vector. If we multiply this vector by a magnitude, we get a vector whose magnitude and direction will match the magnitude that we put into it and this direction. So we're going to just multiply these together. We're going to take x transpose y divided by magnitude of y times u. That means we still have x transpose y on the top. We actually get a second copy of the magnitude of y on the bottom. So we have magnitude of y squared, and then we have this y that was on top here. I'm just going to put it there. And the main reason I'm going to do that is that this thing here, x transpose y over the magnitude of y squared, is just a number. We have a number times y. So whatever vector y is, we just stick a number in front of it, and that will modify y to be whatever projection we want it to be. And this is what we call the vector projection. And notice that because I didn't bother taking out the minus sign, if the scalar projection was negative, when we multiply it by u, it will actually take care of itself. If it's negative, then we're pointing in the opposite direction of y, and we're multiplying y by a negative number to turn it around. So it really does just take care of itself. And so this is what we want. There are a couple other things people will write. The book doesn't do this, but some people write the projection of x onto y. That's what we called it. And some people will also turn this magnitude of y squared into a y transpose y. So they'll write this as x transpose y over y transpose y times y. Just because it kind of, the fact that we have a scalar product over a scalar product is kind of enticing. Okay, so hopefully the break in the video doesn't throw you off too much. I'm going to go ahead and do another video where I'm going to go through some examples and we'll address some things that we can do with the scalar product and orthogonality. So see you then.